In this video, we're going to talk about the acid-base reactions of carboxylic acids and amines. We are first going to look at carboxylic acids, where we're going to look at their reactions when they are dissolved in water, and then when they react with a strong base. For amines, we are also going to look at how they interact with water, and then when they interact with a strong acid. A quick point on terminology here. You're going to see the term ammonia used and the term amine. These two refer to slightly different things. Ammonia is going to refer to when nitrogen is bound to 3 other hydrogens. So anytime you see this compound, we will call that ammonia. An amine requires that at least one of those hydrogens is replaced by a carbon-containing group, shown here by an R. So as long as one of those hydrogens is replaced, but it could be all 3 as well. It doesn't have to be just one. This could be replaced by an R, and this could also be replaced by an R. We will refer to those as amine groups. All right, let's talk about carboxylic acids and how they dissociate in water, and then how they interact with hydroxide bases. So for a carboxylic acid, let's recall that a carboxylic acid is going to behave as a weak acid. So what this means is that it has a proton that it can donate. That proton is always going to be this one right here. This is sometimes referred to as the acidic hydrogen because it's the one that is donated in an acid-base reaction. Okay, so if my carboxylic acid is behaving as an acid, then that means that the other H2O here is going to be behaving as a base. So what this means is that H2O is going to accept this proton, or you can think about it as the carboxylic acid will donate its proton. When it does so, you're going to produce H3O+, and then you're going to produce what we call a carboxylate anion. Because my carboxylic acid has lost a proton, an H+, then what is left behind is a negative charge. And so we have basically a carboxylic acid group that now has lost its hydrogen and contains a negative. Okay, so this is how a weak acid will dissociate in water. It'll dissociate to some extent. It will form a small amount of carboxylate anion, but it will form it. Okay, so this is how it interacts with water. Now let's contrast that with how it interacts with a strong base. So here I have sodium hydroxide is my strong base. And so this acidic hydrogen here can be donated to the OH here. This OH minus is going to behave as a base because it will be happy to accept that proton. When it does so, it becomes H2O, and that's going to be one of our products. And since my acetic acid in this example, but it's any carboxylic acid, when it interacts with a strong base, again, it has donated that proton, and that's why now I have my carboxylate anion again with that negative sign on that oxygen. And then lastly, there is sodium metal in this particular reaction, and so because it's going to form a cation in water, this cation is going to interact with the negative of my carboxylate anion, and this interaction is what we call a carboxylate salt. And again, recall that the term salt is quite similar to the ionic compound. Okay, so sometimes they are used interchangeably, and we're going to use them interchangeably here. Okay, so when you have a carboxylic acid interacting with a strong base, you are going to get a carboxylate salt and water. Notice that both reactions, whether you are putting your carboxylic acid in water, as in the above reaction, or it's interacting with a strong base, recognize that both H2O and NaOH are behaving as bases. So you will be producing the carboxylate anion in both situations. The only difference between the two reactions is the other products that you're going to form. When it's dissolved in water, you're going to form H3O+, since water is behaving as your base here, and it's accepting that proton. In the bottom reaction, you're going to form this salt because there are metal cations in your solution. And then since the OH will accept that proton, you will form H2O. And this bottom reaction is actually a very useful reaction. It's used very often in drug manufacturing because we can basically make soluble any carboxylic acid containing compound by adding some base. Because when we do that, we end up making an ionic compound. And we learned that ionic compounds are very soluble in water. So this is a way to increase the solubility of any carboxylic acid by just adding some base and creating the salt version of your carboxylic acid. All right. Let's do some examples. Here we want to draw the products of the following acid-base reaction that occurs when the following carboxylic acid is dissolved in water. So I know that one of my reactants is going to be water. Okay, so they have provided me with a condensed formula. Whenever I'm carrying out reactions, I think it's good practice and it makes things easier to just draw out what this compound looks like. So let's do that. CH3, it's my methyl group, and I have two methyl groups. Both of those methyl groups are going to be bound to this carbon here. So I'm going to draw that carbon, and then a CH3 group on that side, and one on this one. Right. Now, there's going to be a hydrogen bound to that carbon, as well as this other carbon is going to be bound to that same carbon. Okay, so now that carbon has all its octet rule satisfied. So now that means that these two oxygens here must be bound to this next carbon. In order to satisfy the octet rule, the oxygens must be bound this way to carbon, because lastly, that hydrogen here, by the way that it's written, is telling me that it's bound to that oxygen. So what you'll notice is that the COOH group in a condensed formula is often a carboxylic acid, or is always a carboxylic acid. This is how we write it in a condensed formula. All right, so let's dissolve that in water. And when we do that, we recognize here, if this is my acid, then H2O is going to behave as a base, since we have learned that water can behave either as an acid or a base. In this context, it will behave as a base because I have this acidic hydrogen here that my carboxylic acid will be happy to give as a proton to water. So when that happens, I will lose that proton on my acid. I'm going to just go ahead and condense my structure back just to save a little bit of space. So I'm going to condense those methyl groups back. Oops, CH3, and then I will have my carbon here, and then CH, and I will leave my carboxylic acid group open so that we can see the carboxylate anion. So I have lost that proton there, and now I have made H3O plus, and my reaction is complete. This is going to be my anion here. Okay, let's do the next example. We're going to draw the products of the acid-base reaction. First thing I'm going to do is identify my functional group. I see I have a carboxylic acid, so immediately I know that this H can be donated as a proton. It's an acidic hydrogen. Then I see that I have a hydroxide base. So this means that this acidic proton on my carboxylic acid will be donated to that OH to form water. So I'm just going to go ahead and write that here. And since my carboxylic acid has donated that hydrogen as a proton, it's going to leave behind a positive charge. And then because there's it's going to leave behind a negative charge because it has donated a positive charge. And that means that it is going to pair up or interact with this positive charge from the metal cation from the hydroxide base. So this is going to be my carboxylate salt. And this up here, again, the full term for this would be a carboxylate anion. Oops, not enough space. Carboxylate anion. All right, let's move on to amines. So again, we're going to either see ammonia, which this term just means that hydrogens are what is bound to your nitrogen, or we're going to have amines, where at least one group is substituted with a carbon-containing group, shown as an R group here. Some more terminology. You'll notice that this is specifically a primary amine, and we're going to use the same terms to classify these amines as we did with alcohols, where if your nitrogen is bound to one other carbon, that's going to be considered primary. And because it's a nitrogen, we're going to call that an amine rather than a primary alcohol as we did previously. So what this means is that we can have secondary amines, and that is going to require that we have two carbons bound to that nitrogen. They could be the same carbons or different, it doesn't matter. This is going to be secondary amine. Then that means we can have tertiary amine. If we replace that last hydrogen with a carbon-containing group, this is going to be called tertiary amine. Okay. All right, So with that out of the way, let's look at how these nitrogen-containing groups, whether it's an ammonia or an amine, how they interact with water. They're going to interact with water in the exact same way. Okay, so now I have water here and I have my ammonia. Ammonia is actually a type of base. That's because it contains those lone pairs up top that are able to accept a proton. This means that this water is going to behave as an acid. It's going to be able to donate one of its hydrogens to ammonia, and it's going to donate it as an H+. So when that happens, ammonia is going to pick up an H+, and that's why now as a product, it's going to have a positive charge. Because it took the proton from water, what is left over is your OH, and because it took a proton, you have a negative charge here. So you are left with an OH minus. Then we're going to see that for the primary amine, it is the same reaction because what's doing the reaction is this lone pair, and that doesn't change whether you have ammonia, a primary amine, or any other type of amine. So again, your lone pair will take your acidic your hydrogen or your proton from water, and then you will make again a positively charged ammonium species and your OH group here. This is just OH minus. We're going to refer to these two products with slightly different names. This again is an ammonium ion because all of your substituents here are hydrogens. And when at least one of your substituents is an R group, as is shown here, we're going to refer to this as an alkyl ammonium ion. Recall that the term alkyl just means carbon-containing substituent. It's a carbon-containing substituent. Okay, let's go ahead and look at how this would react, or an ammonium or amine would react with a strong acid. So again, recall that your amine is going to be your base. And again, this reaction can happen with any kind of amine. And then you're going to have an acid. The acid is going to have a proton that it can donate. And the amine will go ahead and take that up through its lone pairs. So when it does that, it's going to gain a positive charge since it has accepted an H+. And then what is left over is the Cl- ion. So here, because we have an H+, or we have a plus and a minus, and this is going to be from your acid, we here have made a salt. And this is going to be called an amine salt. Okay, just one. It's an amine salt. And it's a salt because it's an ionic compound. We have made an ionic compound. So just like we did with carboxylic acids, that we can add some base in order to increase its solubility in water, we can do the same thing with amines. We can add acid in order to create this ammonium ion, or in this case, an alkyl ammonium ion, to create this ion so that when it interacts with that Cl- anion, you are basically have formed an amine salt, which is very, very soluble in water. Let's go ahead and apply these two concepts to different questions. So we're going to draw the products of the following reaction when it is dissolved in water. So again, I have a condensed formula here, so I'm just going to draw it out. What I see is that I have a methyl group and I have 3 of them. So all 3 are going to be bound to my nitrogen. And then this nitrogen will contain these lone pairs, and I'll draw them in since they're the ones that are going to be interacting in this reaction. So now this is reacting with water. So I'm just going to draw it like this so that we can keep track of where our protons are going. And then that means that the nitrogen is going to accept this hydrogen from water. And so it's going to make, well, it's accepting a proton. So it's going to have a positive charge. So now I have a proton there, giving it a positive charge. And then, since my OH is left over, I now have an OH minus ion in solution. Okay. Let's do the next one. We're going to draw the products of the following acid-base reaction. Here they've given me the methamphetamine molecule, and it's interacting with HCl. First, identify your functional group. Your functional group is here. This is going to be an amine because you have nitrogen bound to a carbon on this side, a carbon on that side, and then a hydrogen. Okay. So specifically, this will be a secondary amine. That's not going to have a big consequence on this reaction, but this is just to practice identifying the types of amines that you have. Okay, so here's our amine. Let's go ahead and react. So the first thing that will happen is this hydrogen will be donated as a proton to my methamphetamine molecule. So let's go ahead and draw that molecule out. 1, 2, And now this nitrogen is going to have one more hydrogen. And because it accepted a proton, this is now positively charged. What is left behind is my Cl minus. And again, this will make an alkylammonium salt. So I'm just going to write here, it's a salt, but it's an alkylammonium salt specifically. And this means that this is going to be very soluble. Okay. So again, this is a way to increase the solubility of any compound. Okay. So that is just how acid-base reactions of both carboxylic acids and amines work. A carboxylic acid is an acid, so it will donate its acidic proton. And an amine, it behaves as a base, so it will accept a proton from either water or a strong acid.